All right, it's 8:30, so let's go ahead and get started today. So good morning, everybody. How's everyone doing? Hopefully, did you guys have a good long weekend? Yeah, hopefully everyone had a good long weekend. I spent Monday grading your homeworks, and I'm sure probably a lot of you guys spend the Monday working on homeworks too. But at least we got a break from lecture, and you're able to catch up on some stuff. Yeah, it was hot. Yeah, this weekend was really hot. It felt like I don't know what it's like around where you guys live, but here it was like definitely up in the 110 range, and it was pretty unbearable. I was getting emails from Southern California Edison to cut power usage, but I don't see how that weekend was knowable without air conditioning, especially in kind of a small place like this where the heat really doesn't take that much time to seep in here. But hopefully everyone stayed cool over the weekend. Okay. Okay, so the plan for today is we're going to continue our discussion of hydrostatics. So today we're going to be mostly covering, how do we compute hydrostatic forces on planar surfaces, which has a lot of applications for things if you're designing, like surfaces or boats, that tend to float in the water and need to withstand, pressure forces. So, that's going to be really exciting. I'm hoping we can get into a little bit of buoyancy today. Maybe at least get through at least one example with that. And then probably we're going to finish up the fluid statics unit on Monday. Okay? So I have one announcement to make. I posted the next homework assignment on the Canvas site. And so this homework assignment has to do with fluid statics. So it covers basically everything we did last week with manometry and all the conceptual stuff, the fluid statics, and it's going to cover the stuff we do today, and also on buoyancy. So you should see one problem that represents basically everything that we covered. So it's going to be due next Friday mostly because I don't anticipate us finishing buoyancy until Monday. So I wanted to give you guys a few days after that to do the homework. It's going to be due next Friday at 11:59 p.m. Okay. So before I get started, are there any questions that I can answer from either the lecture last week or the homeworks or just anything about the class? Okay, let's go ahead and get started. And so the next part of fluid statics, I think for a lot of people this is kind of the most difficult part, is how to compute hydrostatic forces on a plane surface. Okay. And so the concept of this, I think, is not too big to understand. Oh, there's a question in the chat. So the question is, will specific weight always be given? 90% of the time it will be given. So a lot of times what fluid you're working with. So if you know the fluid, its density, and so if you know its density, then it's a specific weight. Yeah. But there might be some problems where I give you everything else in the problem, and I'm going to ask you to solve for that specific weight too. So be aware of those kinds of problems. I think for these kinds of problems, just be aware of the situations and the formulas, and just kind of be ready to solve kind of anything in those formulas. I think that's usually a good mindset to have, at least in my opinion. Okay, so for hydrostatic forces on the surface, I think the concept is not too difficult to understand, because what we know already is that when you have a fluid that's static and it's still, there's pressures that develop just from the fact that the fluid has to support all the fluid that's above. Okay, so we already know that pressure, or I should say pressure differences, right? So you have PA minus PB, okay, is equal to minus gamma times the H, right? And so basically, as you go down into a fluid, the pressure is going to increase, right? And let's kind of remind ourselves what the dimensions of pressure are, right? So we talked a little bit about this in the first week of class, but the dimensions for pressure are nothing more than just a force over an area, right? So it's a force that's distributed over an area, right? And so what this means basically is that if we want to compute force, right? And so if we want to compute force from a pressure, right? And so the only thing we have to do is we have to multiply pressure by some area, okay? Right. And so what this tells us is that, as we dive deeper and deeper into fluids, obviously the pressure is going to increase because, we spent a lot of time talking about that. But as the pressure increases, you're going to feel an increased force as well, right? And so the situation that I think maybe a lot of people are familiar with is, deep sea diving, or maybe, a submarine that dives deep into the ocean, right? And I think, as you dive deeper into the ocean, or as a submarine dives deeper, what's known is that as you dive deeper, the pressure is going to increase, and the impression that I think is given by a lot of people is that as you dive deeper, it feels like kind of the water is like kind of crushing you, because you have this kind of pressure force that's kind of pushing on you on all sides, right? And so that's basically the force that I'm talking about here. So, as you dive deeper and deeper into a fluid, the forces that you feel that are almost like kind of crushing you are going to increase because the pressure is going to increase. Okay? And what this unit is going to do is we're going to learn how to compute these forces and what that means for structural design and design of like gates and stuff like that. Okay. And so, I want you guys to kind of go back into your memories of maybe like your physics classes before, where you did like free body diagrams, because we're going to be using a lot of that in this unit. So we're going to be doing free body diagrams of surfaces, computing forces, finding their locations, summing up the moments, all that good stuff that you remember from before, except the only added complexity is that, we're going to be computing forces from the fluids based on pressure. Okay. And so let's start with just kind of a very simple example. So let me draw a tank of water here. And so we have the free surface here, right? And so let's consider just the bottom surface of the tank. Okay. And so at the bottom surface, we know that we have some pressure, okay? And so let's say that we've computed this pressure based on, what we know about the fluid itself, and we know the height, right? And since the bottom of this tank is a horizontal surface, the pressure is going to be uniform across the entire bottom surface. Okay. Okay. And the reason it's uniform across the bottom surface is because it's a horizontal surface, right? So the entire bottom of this tank is at the same depth. And what we know is that from this equation up here is that if you have something that's at the same depth, like you don't change depth at all, then everything is going to be at the same pressure. Okay. And so, if we actually draw out kind of the pressure force that's on this surface, it might look something like this. Okay. Right? And so the way that we can draw the pressure force is that we can basically draw as like a distributed force on that bottom surface, where the pressure is basically distributing a force on that whole surface. Okay. And so because, a horizontal surface is kind of the simplest case because the pressure is uniform all across it. And so if the pressure is uniform all across it, we can basically just use this formula right here to compute the force. Okay. And so what we can do is that we can say, okay, what's the surface area of this bottom surface? And so let's take that surface area multiplied by the pressure which is constant because we're at the same depth. And then from that, we can compute the force. Okay. Are there any questions on this? Okay. Okay, so let's go ahead and do that. So let's say that, we'll call this FR, okay? And so I use the letter R here to denote resultant, okay? And so what that means basically is that, even though this pressure is kind of evenly distributing a force throughout the entire surface, just for calculation purposes, it kind of is more convenient to work with just a single force vector, okay? And so what this means is that basically we're converting the distributed pressure force into a single force vector. Okay. And basically the sole reason is because it's just kind of easier to work with, especially if you're doing free body diagrams. So if you're doing free body diagrams, it's a little bit, inconvenient to work with the distributed force. But if you have just one force vector, then that's kind of the most convenient thing to do. Okay? And just like we saw from the previous page, the way that we compute this resultant force is we multiply the pressure multiplied by the area. Okay? And so if we kind of redraw the picture from before, right? So we have our tank. So instead of a distributed force that goes along the entire bottom, what we have instead is just one single force vector like this. Okay. Right. And so, this force vector has a magnitude of the given by that formula that I just boxed up there. And what we'll see is that, in addition to computing the magnitude of these forces, the other important thing that we need to compute is the location of this force. Okay. Okay. And so, the reason the location of the horizontal force is important is because, not only are we going to do, some of the forces equal to zero, like we typically do in kind of free body diagram equilibrium problems, but we're also going to need to sum up the moments around certain parts. Okay. And to sum up the moments, what we need to do is we need to know the locations of these resultant forces. Okay. So for a horizontal surface, the location is very simple. And so the location of the force, because as we saw from the previous page, the pressure force is kind of evenly distributed across the bottom surface. And so what that means is that the location of this force is simply just going to be at the centroid of the surface. Right? And so that's how we basically, this is kind of the idea of, how we compute a force from the pressure on that surface. So basically what we're going to need for any kind of surface, we need the surface area of that surface, right? So we can compute the area, right? And then from there, we can compute both the magnitude, right? My stylus could stop being weird. Okay. And then from the pressure and from the area, we can compute both the magnitude and the location of the force. Okay. So for a horizontal surface, this is relatively straightforward because the surface is all at the same level. But what we'll see is that we can take these same ideas and apply them to vertical surfaces and inclined surfaces, which are going to be a little bit more complicated because not the entire surface is going to be at the same depth. Okay. But before we move on to that, are there any questions on this?
Yes. So the area in this case is also the magnitude?
Sorry. So the magnitude is this guy. So the magnitude of the force is like the numerical value of the force. So it's you can think of like a force vector. So the magnitude is going to be the length of that vector, basically.
Okay. Okay.
It's
So
the product of pressure times area. So yeah, I drew that arrow kind of weird.
okay. So then we're just grabbing the magnitude out of the resulting force then.
Exactly. Right.
Okay.
Yeah. So this basically is a scalar equation where you're going to multiply a pressure, which is a scalar number, and an area, which is another scalar number, and you get a number from that. And so that number is going to be the magnitude of the force. So the units for this are going to be typically like newtons, right? So that's typically going to be the SI units for force right there. Okay. Any more questions on this before I move on? Okay. Okay, so now let's talk about vertical and inclined surfaces. We're mostly going to be talking about incline just because, once you know how to do inclined surfaces, you can do vertical because you just set the angle equal to 90 degrees. But first, let's talk about, why these situations are more complicated than than the horizontal surface. Okay. So let me draw my tank of water again. Okay. And let me just draw this this fact right here. So we know that as we go down into the tank or we go into deeper depths, the pressure is going to increase. Right? Okay. And so as the pressure increases with depth, what that means is that the forces will also increase. Right? I should say the force magnitude. Okay. And so if we draw kind of the same thing where we did, you know, on the horizontal surface, we kind of drew the distributed force as kind of all having the same magnitude. For a vertical surface, it's a little bit more complicated. Okay. And so if you draw the distributed force on the vertical surface of this tank, you know, it's going to look something like this. Okay. Where at the surface, you know, where the pressure force is, you know, we assume it to be zero, we have basically no force. So that's kind of why this triangle is narrow up there, right? But as we go down into the fluid, you know, that pressure force is going to increase because the pressure itself is increasing, okay? And so this complicates things because we can't just simply say that the force is equal to pressure times area, because, you know, if we go along this surface, this pressure is going to be changing, right? And so we can't just simply do this. So then we need, you know, we need a little bit more sophisticated formulas to help us kind of deal with the situation. Okay, so I'm going to take just basically a general case of an inclined surface, and then from there we can basically generalize that to a vertical surface. Okay. And so this is going to be a derivation. It's going to be a relatively short derivation, but it's, you know, I want to warn you guys ahead of time. Okay, so let me draw the figure here. And this might be the most confusing figure in this class. So kind of bear with me for a second. Okay. So let's say that we have a surface. So this right here, this kind of potato chip looking thing that I've drawn on the bottom, that's going to be our inclined surface. Okay? And I think the thing that's most confusing about this is that we're viewing the surface from the side. Okay? So if you kind of look at my, let's consider my phone here to be the surface, right? And so this is something that, you know, has some kind of surface area, but we're kind of viewing it from the side like this. So it looks really skinny, but if you actually look at it from like this side, it's actually like a surface like this. Okay? And so to kind of illustrate this, what I like to do is, like, not only in addition to this surface right here, I also like to draw kind of what the frontal view of this surface looks like. Right? And so in this particular case, you know, we can assume that, you know, maybe our surface looks like a square, right? So we're basically viewing a square from the side. But because, you know, we're going from the side view, it can also be like a circle too, right? So if you view a circle from the side, you know, it still kind of looks like a very thin strip like that, okay? And so, you know, getting this kind of dimension where we're actually in three-dimensional space, but we're kind of just viewing it from just one perspective, I think that's probably the most confusing thing about this. So I wanted to, you know, take some time to talk about that, okay? Okay, and so the other thing that's confusing, I think, is this guy right here, okay? So we're working in this particular case, we're kind of working with kind of a modified version of our Cartesian coordinates. So normally our Cartesian coordinates, the y direction points vertically upwards. But for this particular case, you know, I'm going to basically rotate the coordinate axes such that the y direction points in the same direction of the surface. So it's basically parallel to that surface. Okay? And so anything that I give in the y direction here is going to be pointed down that surface. Okay. And so the other thing is that, you know, we have the surface submerged in some liquid, so we know the specific weight of the liquid. Okay. And then what we want to find out, or what we want to solve for, is this guy. Okay? And so that guy, very similar to the horizontal surface, is going to be our resultant force. And so what we're going to be interested in is, you know, three things actually. So we're going to be interested in the direction of this force, we're going to be interested in the magnitude of this force, and we're going to be interested in the location of this force. So you know, out of those things, I think the location is going to be the most complicated one to do. And then one thing I forgot to mention is that we know the angle. So this thing that I circled in blue right there, that's going to be the angle at which this inclined surface it makes with the surface of the water. Okay? And so that angle is going to be really important for us as we move forward. Okay. Are there any questions on this? So you know, this figure is a little bit confusing, and in the notes it's drawn a little bit more. In the lecture notes, it's drawn a little bit more clear. But that's basically what we're going to be working with. All right, so question for the chat. So does y have to be stated as negative, or it doesn't matter? So actually the positive y direction is going to be pointed down the surface like this. So negative y is actually going to be pointed out of the water, which I think is kind of another confusing thing. So it's kind of like a fully rotated system where positive y points down the surface.
One quick thing. You mentioned that the angle was going to be given to us, or?
Yes. Yeah. Okay. Most of the time, the angle is going to be given to you, but it could be something that you solve for based on the equations too. Okay. So it's just another variable. So most of the time for these problems, I'll give you everything except for one thing, and you're going to need to solve for that one thing. So I would say most of the time, I would give you the angle, just because the angle is usually some. You know, if you're talking about kind of real life situations, like, you know, the angle is something that you know, but there could be some situations where, you know, you're designing like a basin or something, or you're designing like a gate, and you might need to solve for kind of the optimal angle that makes all the hydrostatics work too. So, you know, for this class, I'll give it to you most of the time, but just be aware that it could be something that you solve for as well.
Okay, thank you.
Yep. Okay. Okay, so let's summarize kind of the things that we're interested in solving for. So we want to solve for the resultant pressure force. Okay, and then we're interested in three things for this force. So, you know, this force is going to be a vector, and so like any vector, you know, it has the following things. So it has its direction. So the vector also has its magnitude, and it also has its location. And so we're going to be solving for basically, or we're going to be deriving expressions for these three things. Okay? So let's start with direction, because direction is kind of the easiest. So the direction kind of, you know, we've kind of implicitly been assuming that from the, just from all the figures here. But the direction of this force, just by the nature of being a pressure force, is always going to be normal to the surface. And so pressure forces act normal to surface. Okay. And so if we draw kind of the, you know, two inclined surfaces here, right? Normal to the surface means that the force just makes a 90-degree angle with the surface. Okay? And so, you know, a resultant pressure force will look like this, where it basically acts directly onto the surface. We have kind of a 90-degree angle here. Okay. So this guy is good. Okay, so we can draw a smiley face. Okay? And so what a pressure force won't do is that it won't act kind of like parallel to the surface. It won't act kind of oblique to the surface, right? There's going to be basically no component of the force that's going to be parallel to the surface. Okay, so these guys will draw an X and draw a frowny face because it's wrong. Okay? So direction is pretty simple, and it's kind of something that we've kind of been implicitly assuming to this time. But I think it's worth it kind of to say it explicitly, in that the pressure force always going to be normal to that surface. Okay, so next let's talk about magnitude. So this is going to be a little bit more complicated, because we can't just straight up multiply a pressure by an area, right? And the reason for that is because the pressure. Remember, the pressure force is going to change as we go along the surface. Okay. And the reason for this is that, remember, because we have an inclined surface, we have some parts of the surface that are at one depth, and then other parts of the surface that are at another depth. Okay. And so what we're going to do is we're going to basically derive an expression that can basically allow us to compute the pressure force for a surface where not everything is at the same depth. All right, are there any questions on this page before I move on? Okay. Oh, question. Okay. Shoot. So the smiley face is just to indicate that we have the pressure force is always going to be normal to that surface. And so what that means is that the pressure is going to act kind of basically directly onto the surface like this. And so the smiley face is just to indicate that this is correct, and then the frowny face is just to indicate that the one over on the right is not correct. Yeah. So we basically the force is not it's never going to be either parallel to the surface or oblique to the surface like this. It's always going to act kind of directly on the surface at a 90-degree angle. Yep. Okay. So let's kind of derive an expression for the magnitude of the pressure force. Okay? And so kind of the the way that we can do this is we can basically perform an integral. So kind of the best way to do this is to kind of break up our surface into lots of little tiny surfaces, and then basically sum up the contributions from all of those tiny surfaces. Okay. So let's kind of draw the same situation where we have kind of an angle theta here. But instead of a big surface, let's say that we just have kind of a tiny surface. Okay? So this is like a tiny baby surface. Okay? And so because it's a tiny baby surface, we can say that the area of the surface is dA. Okay? And so I indicate the D right there just to indicate that it's really small. Okay? And so the other thing that we know about this little baby surface is that it's at a height h. Okay? And the nice thing is because we're working with such a small surface, we can say that this surface is at a uniform depth. Okay? And this is really convenient because now we can basically use the formulas that we have before because we know that it's all at the same depth. Okay? And so if we compute the tiny force that's on this tiny surface, right? We call that tiny force dF. Okay? And we can say that this tiny force is going to be the pressure dP multiplied by the area dA. Okay? Or not dP. Let's just say that is P, right? And so just like before, we can say the force is equal to the pressure times area, but since we know since this is such a tiny surface, we can actually plug in an expression for the pressure using our hydrostatic formula from before. Okay? And so the pressure that's going to be on the surface is going to be the product of the specific weight of the fluid, so gamma, multiplied by h, okay, dA. And so all I did going from the first equation to the second was I plugged in gamma h for the pressure. Okay. So that's good. Okay. All right, so the next step is that we're going to take this expression and express it in terms of our y-coordinate. Okay? Okay? Because remember, our y-coordinate points down the surface like that, right? So since that's kind of our coordinate axes, let's express this guy in terms of that. Okay? And so if we kind of draw a triangle like this, okay, where this guy is theta, we have this right angle, okay? And we know the vertical component of this triangle is h, right? And so if we want to solve for the hypotenuse of this triangle, y, right, we can say that h is equal to y times sine of the angle theta. Okay. And so all I did here was I basically just took the triangle that was given by this guy right here, okay, and then I kind of expanded right here, and I'm basically saying is, you know, now since we know the depth h, what is the distance y that's kind of associated with that? So I'm basically just relating h to y, which is the distance that's along kind of our coordinate axes right here. Okay? Okay? And so let's take this h and let's plug it into the expression above. We can say that df is equal to h y sine theta dA. Okay? Right? And so this df expression here is the expression for the force that's on this tiny surface. Okay, and so in order to basically take this tiny force and expand it to the full force, our next step is we're going to be integrating this over our entire big surface. Okay? Okay, and we're going to do that on the next page.
Professor, should that h next to the y sine theta be the gamma?
Should be gamma, yes. Thank you. Yep. All right, any questions on this before we move on? Okay. And so let's integrate this guy. Okay, so we have df is equal to gamma y sine theta dA. Okay, and so let's integrate this guy, right? And so by integrating the left-hand side, what we get is FR. Okay? And so this is the resultant force. Okay, and so that's basically what we're looking for. Is we're basically looking for this an expression for the resultant force over the entire surface. Okay, and then if we go to the right-hand side and we integrate this guy, we can see that the gamma and the sine theta, these guys are going to be constants, so we can pull them out of the integral. Okay. Okay. And then we have integral of y dA. Okay. So this integral of y dA is actually a very special integral. And you know, it might have seemed strange, you know, the fact that we change h into y, because you know that seems to just make it more complicated. But the reason I did that is so that we can get this integral right here. Okay? And so what's special about this integral is that this is the first moment of area. Okay. So there's you know, there's a lot of moments that you can compute for any kind of geometric object, but the first moment is actually really special because kind of the special name for this that I think is what it's known for is that this is simply just the centroid. Okay? So this is basically the y coordinate of the centroid of that surface. Okay? Okay. And so if we kind of plug that in, we can kind of simplify this expression pretty significantly. So we can say that F R is equal to gamma sine theta times YC, okay? Where YC right here is the, YCA. So we multiply by the area still. Okay? And so what I basically did was I replaced this integral expression with YC, which is the y coordinate of the centroid, multiplied by the area. Okay? And so that kind of simplifies this expression significantly, because now we don't have any integrals, and we simply just have an algebraic expression right here. Okay? And so we can simplify this even further, and to make it kind of convenient for our calculations, is to say that, you know, since we have YC sine theta from our triangle from the previous page right here, where we said that H is equal to Y sine theta, right? So we can apply that same formula here, and we can say that we can define a new variable HC to be simply the depth of the centroid. Okay? And so our final expression for the magnitude of the resultant force is going to be gamma times HC times A. Okay, and so this formula right here, even though it's relatively simple, this gives us the magnitude of the hydrostatic force on any surface. Okay, so we can have a vertical surface, we can have an inclined surface. This even works for horizontal surfaces too, right? And so no matter what kind of surface that you have, no matter how it's inclined, you can use this formula here to compute the magnitude of that hydrostatic force. So it's simply just going to be gamma, which is the specific weight of the fluid, times HC, where HC is the depth of the centroid. So you basically take your surface, find the centroid, and find out what depth that it's at. And then you multiply by the surface area of that surface. Okay. Okay. Any questions on how we arrived at this, this expression here?
Yeah, one more reminder. What was the sub C for again?
So the sub C is to denote the centroid, right?
Okay.
Yeah, so I can definitely repeat that last part. So what we basically saying is that the magnitude of the force, we're basically, you know, we take some surface right here, and normally, you know, we have some kind of distributed force onto it, right? Where it might be something like this. And so if we kind of convert this distributed force into just one resultant force, what we can say is that the magnitude of that resultant force is equal to the specific weight of whatever fluid that you're submerged in, HC, which is the depth of the centroid. So you basically, you know, take your surface, you find the centroid, and you find out what depth that it's, what vertical depth that it's in within the fluid, and then you multiply by the surface area of that surface, and then that gives you the magnitude of the resultant force on that surface. Hopefully it'll be more clear once we do an example, but we have to do kind of one more thing before we do an example. Yeah. But the important thing for the magnitude is, you know, the hardest thing is to find the centroid of your surface, find its depth, and then multiply by A times gamma, and that gives you the resultant force. Okay.
All right. Thank you.
Yep. Okay. So let's move on. So that's the magnitude of the resultant force. So now let's talk about location. Okay. Right. And so location is kind of a little bit of it's a deceptive thing, right? And so what we've done basically right now is that we've taken our, you know, our inclined surface here. Okay. Might look something like this, and we've computed, you know, the magnitude of the resultant force. Okay. And so, you know, because we compute the magnitude of the resultant force from the centroid, it's really tempting to say that the location of this force, or where this force acts, is at the centroid. Okay. Right. It's tempting because, you know, we compute the magnitude from the centroid, so it's only natural to think that, you know, the location of this force will also be at the centroid, right? But I want to tell you that resist this temptation, because it's, you know, it's false. Okay. And why is it false? Right? So the reason it's false is because we know that, you know, the pressure force increases with depth, right? And so what that means is that the parts of the surface that are at a deeper depth experience, you know, higher pressure than the ones that are above it. Okay. And so what this means is that the location of the hydrostatic force is always going to be slightly below the centroid. Okay. And the reason it's slightly below is because, you know, the pressure force is going to be biased towards the bottom, right? And so, you know, if this location right here were the centroid, this FR wouldn't act right here at the centroid. It would actually act somewhere down here. And the reason for that is because, you know, that lower part of the surface experiences higher pressures than up there. And so that's going to kind of bias the resultant force to be slightly below that. Okay. And so the way that we're going to compute the location is we're going to use a sum of the moments formula. Okay. And so, like, the way that you can think of this is because, you know, we have a static equilibrium situation, you know, we know that the sum of the forces on all the surface has to be 0. But another thing is that the sum of the moments have to also be 0. Okay. Okay. And so, you know, this surface here is a rigid object, so it can kind of rotate kind of like this. And so in order for it to stay in place, we can basically say that the sum of all the moments here have to equal 0. Okay. Okay. You know, we can basically just make up kind of one expression for this that we can do. Okay. So we can say that FR times YR is equal to the integral of Y dF. Okay. And so this expression here is basically the representation of the sum of the moments equals 0. So on this left side of the equation, we have basically the resultant moment. Okay. And so the resultant moment is basically the product of the magnitude of our force, which is FR, so we've already solved for that. And YR, this is actually the guy that we're going to be looking for. And so this basically is the location of the resultant force. Okay. Okay. And so I circled in green because that's what we're eventually going to be solving for, right? And then this guy on the right-hand side of the equation, this is kind of like the integrated moment. Okay. And so it's kind of the same thought process in which we did for the previous derivation, where we take a bunch of little tiny areas and we sum up their contributions to the greater thing. But so before we summed up their contributions to the force, but now we're going to be summing up their contributions to the overall moment. Okay. So this is kind of like the sum of all tiny moments. Okay. And so in order for this, you know, these two quantities basically have to be equal to each other. Okay. And we basically want to compute what this YR is from this expression. Okay. And so what we're going to do next on the next page is we're going to work on the right side of the equation in order to work into something that we can recognize, and then we can use that to solve for YR. Okay. Are there any questions on this part? So let's work on that right side of the equation, okay? And so the way we're going to work on the right side is we're going to plug in an expression for df, right? And so just from our derivation from before, we already have an expression for df. So you know that df is equal to gamma y sine theta times dA, right? And this is from before. Okay. Right. And let's also plug in for FR. So FR, we know the expression for this guy just from before, where FR, remember, this is the magnitude of our resultant force. Right? So this is going to be gamma YC sine theta times A. Okay? And so let's take these two expressions here and plug it into our formula, right? And so if we plug this in, we have gamma YC sine theta times A times YR. Okay? This is equal to integral of gamma y squared times sine theta dA. Okay, right? And so all I did to get this expression here was I took these two expressions for the force. So I took the expressions for dF and for FR, and I plugged it into our moment formula from the previous page. Okay, and so let's do some cancellation so we can simplify this guy. And so we have gamma on both sides, so we can cancel those guys out. We have sine theta on both sides, so we can cancel those guys out. Okay. And so what we have here is YC A times YR, okay, is equal to integral y squared dA. Okay. And so now that we have the expression in this form, we've isolated this integral of y squared dA. And so this is also a special integral, right? So remember we said that the integral of y dA was the formula for the centroid of the surface. This integral of y squared dA is also special, and that this is the moment of inertia of the surface. Okay. I remember the first time I saw this in my fluids class, I was like, oh my God, I can't escape, you know, all the statics that I learned before, right? So it all comes back. So moment of inertia here is important, and I'm going to give it the symbol I sub x. Okay? And so from this expression, we can basically solve for YR. Okay? Right, so YR is basically going to be IX, which is the moment of inertia, divided by YC times A. Okay. And so that's our expression here for the location of the static force. But actually, this formula here isn't that convenient. Okay? Because if you recall from your previous classes of working with moment of inertia, you also need to know with respect to what axis this moment of inertia is. Okay? And so in this case, this IX right here, this is the moment of inertia with respect to the surface of the water or the surface of the fluid. Right? And so a lot of times that's not actually that convenient because, if you kind of recall from your statics classes, the way that we compute moment of inertia is we look it up in a table and we kind of just plug in the expressions based on the geometric features of the of that surface. Okay. But when you look up moment of inertia in a table, it's always with respect to the axis that coincides with the centroid. Okay. And so what I'm going to do next is I'm going to use what's called the parallel axis theorem and basically transport this moment of inertia here into the moment of inertia with respect to the centroid of the model. Okay. All right. Are there any questions on this before I move on to the next page? Right, so the WRT stands for with respect to. Yeah. Okay. Okay, so let's employ here the parallel axis theorem. Okay. And so with parallel axis theorem, we can say that Ix, which is the moment of inertia of the surface with respect to the surface, is equal to Ixc. Okay. And so this is the moment of inertia with respect to centroid. Okay. And so this is really convenient because this is something that you can often look up in a table. Okay. Right. And according to the parallel axis theorem, in order to transport this, we have to add the area of the surface times yc squared. Okay. And we know that A is the area of the surface, and yc right here, this is the coordinate of the centroid. Okay. And so if we plug that in, we get kind of the most useful expression for yr. And we see that yr is equal to Ixc divided by yc times A plus yc. Okay. And so this guy that I boxed right here, this is the location of hydrostatic pressure force. Okay. Are there any questions on this? So the next thing we're going to do an example, and you'll see these equations in action. So I know we've spent a long time today deriving these equations, but hopefully once you see them in action, then they kind of make a little bit more sense. Okay. So let's do an example. And so this example is kind of a very classical hydrostatics problem. So basically, we're going to have an inclined surface, and our inclined surface is going to be a gate. Okay. So let's do a circular gate submerged in water. Okay. And so the geometry looks something like this. So we have our surface like this. Okay. We have an inclined surface, right? And this incline has an angle of 60 degrees. Okay. And then in the middle of the surface right here, we have a gate. Okay. So our gate's going to look like this. Okay. Our gate also has a stopper. Okay. And then the hinge of the gate is given in the middle of the gate. Okay. And if we look at the frontal view of this gate, it looks something like this. Okay. So basically, just looks like a circle, and there's kind of a shaft in the middle. Okay. So if you can imagine this, it looks like a Pokeball. But basically, what this gate is, it's basically a circular surface, and it rotates about kind of a hinge in the middle. So it basically can do like this, if you can imagine. Okay, and so let's put some dimensions in here. So we know that the gate has a diameter of 4 meters. Okay. Okay. And we also know the depth of the gate. Okay. And so we know that HC is equal to 10 meters. Okay. And so that's going to be the depth of the centroid. So because the shaft kind of passes right through the middle of the gate, then the depth of the shaft is also the depth of the centroid. Okay. Okay. And so let's compute two things. So the first thing is let's compute the magnitude of the resultant force. Okay. So we're basically just going to apply the formula that we did before. Okay. and let's find the location. Okay. And then from the magnitude and the location, what we can compute is the moment that's needed to open the gate. Okay. And so what we're going to do is we're going to apply the equations that we went over today to basically compute all of these guys. Okay. Are there any questions about the problem setup or the problem geometry? Okay. So let's go about doing it. Okay. So let's start with the magnitude. Okay. So this is relatively simple, and we actually have everything that we need here. Right. Oh, I forgot to mention that the fluid is water. Okay. So our gamma is going to be 9,800 newtons per meter cubed. Okay. Okay. So for the magnitude, we're just basically going to plug into the formula that we had before. So the formula is Fr is equal to gamma times HC times area, okay? And so we have everything that we need here. So we know that the gamma is equal to 9,800 newtons per meter cubed, okay? We know that HC here is 10 meters, okay? And then now we need to compute the area of that surface, okay? Oh, question. So is staggered just for free body diagram visualization? Yes. Yeah, it's just for visualization purposes. Okay, and so now we need to compute the surface area of the surface. So since it's a circle, the area of the circle is basically going to be pi r squared. But since we're given diameter, the way that we can express this is pi over 4 times d squared. Okay, and so d in this case is 4 meters. Okay, so we see this is 4 meters squared. And so we just plug all those numbers in, and we get a force magnitude of 1, 2, 3. 1,504 newtons. Okay. Okay. And so since we're given the depth of the centroid of this problem, then the magnitude of the resultant force is pretty simple. Okay. Okay. So any questions on how we computed the magnitude? Okay. Okay, so now let's do location. So we know that location, YR is equal to IXC divided by YC A, okay, plus YC, okay. And so we're basically going to plug into this formula, you know, in order to compute YR, okay. And so you have to be a little bit careful here because remember the location is given by YC. And so this is not HC, okay? So don't just simply plug in the depth of the centroid because they're not the same thing, okay? And so the only case where HC and YC are the same is if you have a completely vertical surface, okay? But since we don't have a vertical surface, we have an incline, we need to convert this HC into YC, okay? And so thankfully it's pretty simple. So we're basically going to use the angle that's given to us, okay? We can say that YC is equal to, YC is going to be equal to HC divided by sine theta, okay? Where theta is given in this case as 60 degrees, right? And so if we plug in all the numbers, we get YC is equal to 11.55 meters, okay? Okay? And so we know the area already too, because we just computed the area up here. So area is just going to be simply pi over 4 times the diameter squared. Okay. And so the last thing we need is the moment of inertia with respect to the centroid. Okay. And so if you look up in a table of moments of inertia, and we look up the moment of inertia with respect to the centroid of a circle, what you get is pi r to the 4th divided by 4. Okay. And so this is you get from a table. Okay. So the table that I typically use is from Wikipedia. So typically I just Google search as moment of inertia of a circle, and then Wikipedia is always the first link, and you just look at the table, and that's the formula that you use for that. Okay. And so if you plug in the numbers for this, where the radius is just going to be 2 meters in this case, you get 12.57 meters to the fourth. Okay. Right? And so now that we have YC, we have IXC, and we have area, we can plug in these guys and solve for YR. Okay. Are there any questions on this page? Okay. Okay, so if we plug in all the numbers, we get YR is equal to 11.64 meters. Okay. Okay. And so along the Y axis, then the location of the centroid is going to be 11.64. Okay. And so let's visualize that. Okay. And so we have our gate here. Okay. Okay. And so we just computed the depth of the centroid, or not the depth of the centroid, the Y coordinate of the centroid. And so the distance from the surface of the water to that centroid along the same plane of the surface, that's going to be 11.55. Okay. But the location of the centroid of the pressure force itself, that's going to be given by YR, right? And we know that YR is always going to be slightly bigger than YC. Okay. Okay. And so the location of that resultant force is going to be 11.64 meters. Okay. And FR is given by you know, that force, or the force that we computed in part A. Okay. 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 And so the last thing that we're going to compute in this problem is the moment that's required to open the gate. Okay. And so remember from the problem before, we had a stopper right here. Okay. And so what the stopper is doing is basically, because this resultant force is putting something that's below the hinge, what that's doing is it's forcing the gate to kind of try to rotate counterclockwise. Okay. So the zoom is not being staticky. I just had some phlegm in my throat. Okay. And so, you know, in order to open the gate, what we need to do is we need to apply a moment in the opposite direction. Okay. Okay. And so that moment is going to be clockwise. Okay. Okay. And so that moment is basically going to be equal to the moment that this FR is putting on the gate already. Okay. And so what we need to do is we need to compute the moment FR is putting on gate. Okay. And so remember, moment is equal to force times some distance. Okay. Where this distance right here is distance to the hinge, or distance to the part where it's going to rotate about. Okay. Okay. And so in this particular case, our distance to the hinge is based, since the hinge is located at the centroid of our gate, the distance to the hinge is simply just going to be YR minus YC. Okay. And so if we plug that in, we can say that the moment is equal to FR times YR minus YC. Okay. Because that's basically going to be this distance right here. Okay. That's the distance from the force to the hinge. Okay. And then what we get from this is 110835.36 Newton meters. Okay. So in order to open this gate, we need to apply a clockwise moment, basically in the opposite direction of that force, equal to basically 110,865 or 835 Newton meters. Okay. And so that's, you know, this is kind of a simple kind of last part of this problem, but it kind of shows you, you know, why you're interested in kind of the magnitude and the location of this force, because it allows you to compute things like moments, which are, you know, important to the design of gates like this. Okay. All right, any questions on this example?
Yeah. For the moment, we're always applying clockwise. What if is there ever been a situation where we go the opposite direction?
Oh, absolutely. And so a situation that might be opposite is if the gate is kind of inclined in the other direction, right?
Yeah.
So you have a gate that's like this, and you have a force that's like this, right?
Mm-hmm.
And so in order to kind of open this gate, you have to apply a moment in the counterclockwise direction.
Okay.
So yeah, it depends.
Okay.
It depends on the geometry of the situation, on what direction the moment has to go.
Okay, but in general, we can just assume that whatever direction the FR is going, we just use the moment in the opposite direction.
Exactly. Right. Yeah.
Okay.
Mm-hmm. Yeah. So in this case, the FR, you know, if you kind of rotate this guy right, FR wants to push the gate and rotate it this way. So that's counterclockwise, right? And so in order to open the gate, we have to apply a moment in the opposite direction, which is clockwise. Yeah. Okay. Okay. And so, so if you look in the lecture notes, there's another section after this called, you know, how to compute hydrostatic forces on curved surfaces. So, you know, I'm going to leave that to you guys to review. But since we're not covering in the lecture, I'm not going to ask you about it on the homework or test you on it. But I think, you know, what's probably more valuable for the last 9 minutes of class is that we do one more example of, you know, how do we do, you know, hydrostatic forces on a planar surface. Just because, you know, we did one example here, but I think, you know, doing another example will be, I think, a bit more valuable. Okay? And so this is the next example in the notes, but actually, you know, the example that I have there is actually incorrect. So I've uploaded another PDF of the same problem, but with the correct solution. Okay? And so for this example, you know, look at the second PDF where I've uploaded a PDF called More Hydrostatic Examples. And so this is basically the example that I'm going to cover here. Okay. And so in this example, we basically have a square gate between two fluids. Okay. And so the geometry looks something like this. Okay. And so we have basically a square gate. And so the square gate is going to be hinged at the center of the gate. Okay. And so on the left-hand side of this gate, we have water. Okay. And the specific weight of this is going to be 9,800 newtons per meter cubed. Okay. And then on the water side, we actually know the depth. Well, actually, I kind of drew this incorrectly. Sorry about that. So the depth of the water actually goes up to the hinge of the gate. Right? And so the depth of this water, oh, wait a second. Oh, I had it right the first time. Sorry about that. And so the depth of the water basically to the centroid of this gate is known. So this is 1.5 meters. Okay. And on the other side of the gate, we have a different fluid. So let's say that we have oil. Okay. So the specific weight of the oil we're going to assume is going to be 5,000 newtons per meter cubed. Okay. So it's not as dense as the water. Okay. But what we don't know is this guy right here. Okay. And so what we want to solve for is basically the height of the oil that basically holds this gate in equilibrium. Okay. Okay. And so we also know the size of the gate. So the size of the gate is 3 meters, okay? And the fact that it's a square gate, okay? And so the fact that it's a square gate, we know that the gate basically looks like this. Okay? So this is the frontal view of the gate. Okay? And so what we want to solve for is solve for the HO, or solve for the depth of the oil, that will hold this gate in equilibrium. Okay, and so basically what this means is that we're going to compute 2 moments. We're going to compute a moment from the water side and a moment from the oil side, and then those 2 moments have to cancel out. Okay, and we're going to use that to solve for HO. Right? All right, any questions on this, on just the setup of the problem? Okay. Okay, so let's start with the water side, because on the water side we know everything on that side. Okay. And so just like we did with the gate problem, you know, what we want to compute first is the magnitude and then location of the resultant force. Okay. And so let's go ahead and do that. So we know that the magnitude of the resultant force, Fr, okay, and we'll say this is FRW is equal to gamma W HW times A. Okay, and so we have all of those things, and we plug it in. We get 300 newtons. Okay, and then the location is given by HRW is equal to IXC all over HCA plus HC. Okay, and so notice in this problem I'm using H instead of Y, and that's the reason for that is because we have a vertical surface, right? And so when you have a vertical surface, H and Y are in the same direction, so we can just compute those guys. Okay? And then for a square, we know that IXC is equal to 1 over 12 L squared, okay? Where L is the, L to the 4th, I mean, where L is the length of that square, okay? And so you plug everything in, and you get RW equal to 2 meters, okay? Okay? And so the moment is simply just going to be FRW times HRW, okay? So this is equal to 264,600 Newton meters. Okay. Right. And so, you know, just like we did with the gate problem, you know, we computed the magnitude and the location of the force. The location is a little bit simpler in this case because it's a vertical surface, so there's no angle for us to play with. Okay. All right. Any questions on this on the water side?
The inertia, is that length being to the 4th power, or is it supposed to be squared?
Yeah, it's a 4th power. Yeah. Okay. So very quickly, let's do the oil side. Okay. And so we're going to follow the same procedure as before. So we're going to find the magnitude and location of the pressure force. Okay. Except in this case, we don't know HO, so it's going to be an unknown in the equation. Okay. So let's start with FRO. Okay. So FRO is going to be gamma O A times HO. Okay. And so since we don't know FHO, we can leave it as a variable. Okay. So it's going to be 45,000 HO. Okay. And so the location HRO, okay, will be equal to IXC divided by AHO plus HO. Okay. And so we plug these in, and we get 3/4 HO plus HO. Okay. Okay. Is that an arrow subscript 1 for H? Let me finish up this example, and then I'll answer any questions. Okay. Just because we're running a little bit short on time. Okay. And so the distance to the hinge, you know, we need to compute this for the oil side. So for the water side, it was a little bit simple because the water just came up right up to the gate. But for the oil side, because the HO is going to be higher, we need to compute this distance. Okay. So this distance is going to be our location right here. So 3/4 HO plus HO, okay, minus HO minus 1.5. Okay. And so this is HRO. And this right here is the distance from oil surface to gate. Okay. And so if we compute this, D is going to be equal to 3/4 HO plus 1.5. Okay. Right. And so we're out of time, so I'm going to go forward a little bit, but you know, you guys can check out the recording later. Right. And so the next thing is that we need to compute the moment from the oil pressure force. Okay. So this is MO, which is equal to FRO times D. And so this is equal to 3,000 or 30,000 plus 67,500 HO. Okay. Okay. And so now that we have the moment on this side, we can set it equal to the moment from the water side, which is what we computed before. So it's 264,600 equal to 30,000 plus 6,500 HO, solve for HO. Okay, we get HO is equal to 3.476 liters. Okay. Right. So I apologize that I rushed a lot through that last example, but we're about 3 minutes over time. So I'm sorry, everyone, you know, for keeping you a little bit. But that's basically, you know, hydrostatic forces on surfaces. And so the only thing we could cover, it was hydrostatic forces on planar surfaces. So you don't have to worry about curved surfaces showing up in any exam. Okay? So thank you everyone for showing up today. I'm sorry I ran a little bit late and I rushed a little bit at the end. But if you have any questions on this example or anything else, you know, I'll stick around. And then we have office hours tomorrow for that as well. Or if anything, you can send me an email. Okay. So thank you everybody for showing up for this short week. Have a great weekend, and I'll see you guys on Monday.
Could you go back one page?
Yeah.
Thank you.
Mm-hmm. Yeah, so I'll stick around for a while, you know, if you guys have questions, but, you know, I don't want to keep you guys, especially if you have another, you know, other engagements to get to. So, so thank you, everybody. I'll see you guys next week.
Thanks, Professor.
Yep. On the water side, the subscript for H is W. So that's basically just the depth of the water. Yeah. So that's going to be the 1.5 that's given in the problem. Yeah. So it's H. So I do HW just to denote that it's the depth of the water side. Under location. Oh, so these are C's. So I basically was saying that these are basically the depth of the centroid, but they're basically the same as HW that's given in the problem. Yeah.
Wait, sorry, Professor, can you hear me?
Yeah.
Yeah, it's location. It's the first H on the left side of the equal sign.
Oh yeah. So that's HRW. So that's the depth of the resultant force. So I'm using the subscript R to basically denote resultant, right?
Oh, okay.
Yeah. So I do H sub R comma W to say the location of the resultant force for the water. Yeah.
Oh, okay. Thank you.
Do you guys have any more questions about the lecture today? Okay. So if you guys have any more questions, definitely you can email me, or you can pop into office hours. I'm always happy to answer questions. But if not, I'm going to end the call. So thank you guys again for tuning in, and I'll see you guys on Monday. Oh, Joshua, did you have a question?
Yeah. So, what was the part that says distance to hinge? So, I didn't get to write that down. 3/4H plus 1.5. Okay. Explain that part again.
Yeah. So basically, in order to compute the moment, basically moment is always equal to a force multiplied by a distance to the hinge, right? And so what we want to do, so we computed the magnitude of this pressure force from the oil, right? And so the pressure force is going to be acting like this. Okay. And so in order to compute the moment, we need to compute the distance in between this pressure force right here and the hinge that's right here, right? And so what we just computed was HO, where HO right here is the distance from the surface of the water to the resultant pressure force, right? Oops. And then the other thing that we know is the distance from the surface of the water to the hinge itself, right? And so the distance to the hinge is just going to be kind of the difference in between these two guys, which is what this is right here. Yeah. So the main thing is we want to compute the distance between the resultant pressure force and the place on which the gate's going to rotate from, which is the hinge of the gate.
So that's from the bottom of the surface to the hinge. That's the difference.
Yeah. So it's from the top. So HO that we computed here, or that we want to compute, is the distance from the top of the water to the location of the pressure force.
Oh, okay.
Yeah.
I was just saying I drew my arrow on the hinge, which is wrong because that's the force is not there.
Yeah. So the force should be slightly below the hinge, just so it can impose a moment onto the gate.
Right, because you can't do a moment on the actual hinge itself, otherwise.
Exactly. Right.
I see. Let me redraw that. See, I would have drawn that wrong. Okay. Okay. And then that's that difference in height. The HO is on the actual force, and then the other distance is on the hinge.
Exactly. Yeah.
Okay. So I can write down HO, the distance from the oil to the force. All right. Thank you. I'll look this over.
Okay. Yeah. If you have any questions on it, just shoot me an email, and I'm happy to answer.
All right. Thank you. I appreciate it.
Yep. Have a good weekend.
Goodbye. You too.
Preston, did you have any more questions? think Preston is AFK. Okay, I'm going to end the call.